Okay, well, welcome everybody to fourth week's Philosophy of Physics seminar, and it's a real pleasure to introduce Sam Fletcher as this week's speaker. So, as Sam's title slide tells you, he's mainly from the University of Minnesota, but luckily for us, he's a visitor in Oxford this term and next. This term as a visiting fellow at St. Cat's, and next term as a visiting fellow at Corpus. Sam did his PhD at UC Irvine, and which was where I first met him on a very enjoyable, partly thanks to Sam, visit to California many years ago. And he has written very widely in philosophy of physics with a kind of predominant interest in space-time topics and pioneering work in the topology of state spaces, solution spaces. So Sam, it's a great pleasure to have you speaking today on relativistic spacetime, dependence and ontology.
Thanks so much, Ollie. About 1.25 years ago was the first time that I stepped into this seminar room, and much more nervous than I was today, gave a seminar to the temporally prior counterparts of you, which are overlapping to some physical extent with some of you. And so it's really wonderful to be back in the same place and to be speaking to the Oxford folks once again. The topic today that I'm going to be giving you some info about is a part of a book project that I'm working on. So this is a screenshot from the table of contents as of a couple of days ago with some redactions. And as you can see, the book project is on the foundations of general relativity. There's going to be 8 chapters to the project. After introducing a kind of foil interpretation of general relativity in the first chapter, I go on to use that foil as a test case for making comparisons and adjudications across a range of issues. The second chapter will be about the role of representational principles. That is to say, principles that we use to connect the mathematics of the theory to the phenomena and the worlds and the possibilities we think is the subject matter of the theory. Today, I'm going to be giving you the first version anyone, including me, has ever heard about chapter 3, which is the ontology of the theory and also the dependence relations in the theory and how to interpret the dependence relations. The fourth chapter is going to go on to talk about the role of other types of principles, non-representational principles, principles that have to do with how certain choices or structures are justified, how they might be constrained with respect to a large class of possibilities, and how the theory relates to theories that came before it. The fifth chapter talks about energy and the notion of energy in general relativity using gravitational waves as a test case to understand how energy may be different or similar to energy in theories that came before. Chapter 6 goes to the theory's implications for time and causality, before chapter 7 goes into things that are quite specific to GR, new phenomena having to do with singularities and black holes, before I get to the last chapter, which is a kind of coda reflecting on how these interpretive issues may change and how choices for these interpretive issues affect the program for a quantum theory of gravity or some unification of quantum theory and gravity. So today I'm just going to be focusing on, in a certain sense, the metaphysics, or at least what I might call metaphysics. I'm going to try my best to give an interpretation of what the theory is talking about and how the different things the theory talks about depend upon one another. So about the first quarter will be on my methodology, kind of how I see the theory, the formal mathematical theory, as providing a guideline or constraint to how we interpret the theory. About half of the talk is going to be on this second section, where I try to give a positive account of what I think the theory is saying, interpreting the objects in the models. And then I'll try to address a number of queries that some of you might have, unanswered questions, and also make some comparisons of my positive account with other positive accounts that people have proposed. And then the last quarter, we'll focus on the notions of dependence in the theory. In addition to talking about the stuff that there is, we're also interested in knowing about what stuff depends on what other. I'll try to give a positive account for that and say as much as I can towards queries that one might have in comparisons with other sorts. Now, there's some aspects of this which are unfinished, and my hope is that some of you can help me with if you have any of your own ideas to suggest about how to finish the unfinished parts. I'll definitely explicitly flag those when I get to them. Okay, so I take the models of the theory. These are the individual mathematical structures that describe either possible worlds or possible states of affairs as a guide to what the theory says about the world. So the objects in the models are going to give us a guide to the theory's ontology. The formal mathematical relations between the objects of various sorts are going to be a guide to the properties and physical relations that those objects manifest. And the mathematical functional dependence of objects of objects to other objects will be some guide to the physical or metaphysical dependence of the objects. Asymmetric functional dependence in this sense can be a guide to relative fundamentality. Now, why a guide? Why not determine? Well, we use models in part to make our reasoning more precise and to ward off ways of fooling ourselves. Let me give you an example about why we should use our models as a guide. All right, I want you to relax for a second and think about trying to imagine a planet that's so windy that at every place, not just in the seminar room, but at every place, there's a breeze blowing. Well, you can't, right? And it's not entirely obvious, unless you've studied a bit of mathematics, why, in fact, you can trick yourself into thinking that you can imagine such a planet. The hedgehog theorem, or sometimes called the hairy ball theorem, tells us, for instance, that there's no way for us to comb the hairs on the ball in a way such that no hair is sticking up. If you think of each of the hairs as describing the direction of wind at that point, what that means is that there's no way of assigning a velocity to wind on every point of the planet that's non-zero. Some hair is going to have to stick up and be zero. So these sorts of examples, these simple examples, are supposed to show how the models, as they're described by the mathematics, put constraints on the possibilities that they describe. And if we don't allow ourselves to be constrained in this way, we can fool ourselves into thinking that we've imagined a possibility that in some subtle way is not actually internally consistent. So when models guide metaphysics, they underwrite consistency. Insofar as we have confidence in the consistency of the mathematics that's used in the construction of the models, that gives us a reassurance of the consistency of the metaphysics. But why only a guide? Why can't the models determine the metaphysics? There's a few reasons. One is that, at least on my view, modeling is a human activity. We model for many, many purposes besides metaphysics. We can have features in our models that we don't think correspond to real things in the world or real properties. Mathematical dependencies between objects that we actually think don't or not supposed to reflect real dependencies in the world. But we have them nonetheless because we use models for prediction or calculations or convenient description. Another reason is that models typically abstract from and misrepresent their targets in some ways. Models don't represent all the features of the things that we're interested in. So they can have things that are missing, and they can misrepresent their targets. That's to say that they can represent a phenomena in ways that they aren't. When those sorts of things occur, right, and we only use the structure of the models as a way of doing metaphysics, we can lead ourselves into errors as well. So this is why I take the models of our theory as a guide, but only a guide to how we interpret our theories. So in particular, modeling and interpretation are kind of dialectical interlocutors. What I mean by that is that oftentimes we'll start with a collection of models. We'll try to describe an interpretation of them for some phenomena of interest. We realize that there's something wrong with the collection of models. Maybe it doesn't have enough structure. Maybe it has too much. Then we change the models and we try again. And through this comparative process, we try to arrive at some place that you're satisfied with, some sort of reflective equilibrium that could and then be disturbed at some future point by some new insight that you have. Okay, so all else being equal, given an interpretation, right, its ontology properties and dependencies should find formal correlates in the models. And given a set of models, their interpretation should reflect the model's objects, relations, and functional dependencies. These are the two methodological principles that we use in coming to that reflective equilibrium. Sometimes we won't be able to implement one of these perfectly well, but we should just recognize when we do so. Okay, so that's a basic idea about how I see the project of interpreting the theory. So now let's start with the theory itself. So one of the things that general relativity does is it describes the structure of space, time, and gravitational phenomena. A kind of pared down description, mathematical model of this consists of the following sorts of things. One is we've got a smooth four-dimensional manifold. This is a structure, a geometrical structure, that in the small looks like a chunk of R4, right? A chunk of the real line quadruply producted with itself. So a four-dimensional chunk. And if you put enough chunks together, right, you form a bigger space that may not globally be R4, but may locally look like it. The interpretation of the manifold is that its points represent the atomic events. That is to say, events that have no proper parts to them. In addition to this collection of events, we also have a Lorentzian metric G. What this structure does is it does two things. One is it assigns at the tangent space at every point, but you can think of these cones here as being more or less being depicted at a small region of spacetime. These cone structures divide the directions in lines of events. So we have, for example, here depicted two different lines of events. And lines of events can thread through the cones, they can skate along the cones, or they can go outside of the cones. The ones that thread through the cones, right, are going to be collections of events, histories of events, if you'd like, that have a duration. And what the metric does is, in addition to assigning these cones, also assigns durations to these lines. And it assigns physical lengths to the curves that lie outside of the cones. If you like, you can think metaphorically of the cones as describing the edges of the cones as describing the maximal speeds or trajectories relative to anything that any object that experiences time or that has time in its description of its histories could ever undergo. So for instance, you can imagine a vertical direction here as a direction that involves lapses of time, and the horizontal directions, roughly speaking, as directions or collections of events that don't have any duration, but are extended, are collections of events that have extended lengths. So intuitively, if you want to think about that, think of a snapshot of my arm. Let's see if I can get it in the picture here. Okay, a snapshot of my arm. There's an event here and here and here and here and here and so on, right? At a particular snapshot, that collection of events, we can add them all up to get a length for my arm, right? You'll notice that my arm is extended, right? Fortunately, it's not point light, right? And so we get a positive number for the length. The way that that would be represented would be as a particular curve that threads outside of the light cones in this picture. And we have one more collection of things. We have one more thing so far. It's going to be a collection of matter fields. Mathematically, these are going to be sections of a certain bundle, usually a principal bundle. If you're not familiar with that terminology, don't worry about it. Just think about it as a field like an electric field or a magnetic field that gets assigned to each event. So in a certain sense, each event is about the values of these fields that are coincident together. Now, any space-time model requires these elements. Sometimes we want to add a bit more. So you want some more? We can do some more. In addition to a structure, the metric that's going to assign durations to collect certain collections of events and lengths to others, we also want a notion of change. We might be interested in the question, does this field, like an electric field or magnetic field, change over a collection of events? This upside down triangle, this nabla, sometimes called a covariant derivative operator or an affine connection, is an object that allows us to describe notions of change within the theory. And not just notions of change for specific things, but notions of change for any sort of field that we want to describe. The reason why this object here is on the more slide and not on the previous slide is that this particular object is determined by G. The way that it's determined by G is that it is an extension of a notion of change that we can get from G. So for very special types of fields, we can measure the change of those fields along curves using G. What nabla does, what the covariant derivative operator does, is it allows us to extend that notion of change to a larger class of fields. It always agrees with the metric when they are applied to objects that they can both apply to, but it applies to more objects. So this covariant derivative operator or affine connection extends the notion of change that we get from the metric. Sometimes we also want to have extra space-time structure. Extra space-time structure, in addition to the things that I've described, might include something like a temporal direction. A temporal direction is going to be the thing that picks out the arrow that you see at the top of the two lines. An arrow indicating which direction is future and which is past. Without the arrow, there's no saying which is the future and which is the past. A temporal orientation, for instance, picks out for each double cone. You might imagine coloring in each double cone, one of the two, in a continuous way across the whole space-time, a direction which is the future. And there's others that we can pick as well. Another thing that we might add are certain curves. Curves that thread through the light cones. These are the ones that have durations, or ones that start along the light cones, right? So-called null curves. These jointly together are called the causal curves. And we might add those to represent specifically particular particles of matter. In the former case, massive particles, and in the latter case, for the null curves, light rays, point-like light rays. Now, importantly, for reasons that will become clear later, these sorts of objects have to be so-called test objects. They experience, as it were, the structure of durations and times as much as their dynamical equations say that they do, but they don't themselves contribute to the changing structure of times and durations. The significance of that has to do with how, in the theory, the presence of matter and momentum is correlated with the structure of times, spaces, and their changes. The simplest way to write that correlation is with Einstein's field equation. The Einstein tensor that you see on with GAB there is a structure that encodes how the metric tensor has a how the metric tensor makes the structure of durations and times, if you don't mind the phrase, a bit wibbly wobbly, right? A little bit timey-wimey, instead of being something straight and narrow. I'm being a bit metaphorical here because I don't want to get into too many of the details about how the structure is determined. The main important thing here is that there is a correlation between how the structure of durations and times bend and the presence of energy and momentum. That's what that TAB describes. One of the things that's important about this is that it shows that the structure of times and change locally within spacetime determines but doesn't define the local presence of energy and momentum. You can see that because if geometry of spacetime, which is describing the wibbly wobbliness, right, of the structure of durations, is the input to G, we can see that once we have GAB, that determines TAB. What the Einstein field equation, though, does is that it correlates matter with the structure of these things. And the reason why is that it doesn't tell us what matter fields there are or how those matter fields contribute to energy and momentum locally at a point. It also allows for an interpretation of gravitation, right? And all its manifestations and effects as this correlation. So the effects of gravity on this view, right? There is no extra object in the theory, which is called the gravitational field, right? No extra object in the theory, which is called the gravitational potential. Gravity and the manifestation of gravity, right? We find in the way that energy and momentum correlate with the structure of time and space. Now, in the things that I've described so far, there's two sorts of sorts of things. Space-time structure and material fields and particles. The space-time structure, which includes the G, the metric field, and any extra structure that I represented by the chi, like a temporal orientation, these represent spatiotemporal concepts. And usually they are structures on the field that don't have a rule that says they add to energy and momentum locally at points. Whereas material fields and particles represent the stuff that events are at least potentially about. They are the things that usually do contribute to energy and momentum. Why usually? Well, it's going to depend on our understanding of test matter that I alluded to before. Test matter describes matter that we think describes stuff, but we consider doesn't contribute to energy and momentum. It's a kind of a paradoxical thing. It's one reason why we might be skeptical about whether we should really allow for test matter in our theories or not, or we should give it some sort of special interpretational status. If we set aside that type of matter and we demanded that all matter contribute to energy and momentum, we have a very nice separation, or at least criterion for what counts as space-time structure and what counts as material fields and particles, according to whether or not the fields contribute to energy and momentum. I should mention that there's no logical requirement that these two sets be disjoint from one another, actually. It's entirely possible that you have some sort of structure that represents durations or lengths or changes in fields across events. that also contributes to energy and momentum. In practice, that doesn't happen so often, but there's nothing logically precluding it on this interpretation of general relativity. Okay, so a natural question arises. Okay, Fletcher, you've been saying a lot of things about how you interpret these objects, but what do you say about this old debate, substantialism and relationalism? This debate is about whether or not space or space-time and its structure exist independently from material things or not. Substantialism says yes. The name, of course, comes from the old idea that such things had to be substances in the metaphysical sense. We no longer think that things that exist so independently have to be substances, but the name has stuck. The relationalist denies that, usually affirms that space-time and its structure are just abstractions from or derived from relations between material things, and perhaps the parts of material things. So here's a sort of acid test, usually, if you have an interpretation that's guided by models that allows us to know whether or not the theory is better interpreted as substantivalist or relationalist. Do we permit events in the case of the theory that I'm describing, or whole spacetimes, whole collections of events, with only space-time structure and no material things? If you say yes, then it's substantivalist. If you say no, then it's relationalist. I think it's interesting that in what I've described so far, the question is not decided. In a certain sense, either could work if you just add the right assumptions. So suppose you wanted a substantivalist version of the interpretation that I've gave. There's no change needed to the models of general relativity or their interpretation. The significance of that, of course, is that general relativity has lots of models that seem like they describe empty space without any matter to it, that have their own dynamical properties. Not all of them are identical with one another. Some of them are very boring, but some of them include rogue gravitational waves drifting through the universe. Now, a negative for this interpretation is that it puts a bit of a strain on the elements of M as being events. It's natural to interpret an event as a coincidence of material things. In order to make this interpretation substantivalist, we would have to expand our conception of what an event can be. Here, an event would not just be a coincidence of material things, but a possible coincidence, but not necessarily an actual coincidence of material things. But you could also give a relationalist spin to this interpretation. You would affirm events are always coincidences of material things, but we have to do a little bit of extra work to understand models in which matter doesn't appear. Models that have events that have no explicit material subject. For instance, they may not have any fields present at them. Or if it's a model that only has particles, there may be no particles present at those events. They must be understood as abstractions from models that do have them. Abstractions, for example, models that have test matter that's pervading through the universe. This is important because remember that the models that we use in our theories, right, sometimes abstract away from things of interest for reasons of simplicity, pragmatic reasons. On this interpretation, what we would do is we would insist that no, really, all of our models at every event have some matter present, but we've abstracted away from that matter in the presentation of the models. And that matter either contributes so little to energy and momentum there or doesn't contribute at all that we can keep the presentation of the model as it is. I think the significance of this says a little bit about why some commentators have remarked that in the context of general relativity, the debate between substantialism and relationalism seems like it involves very fine distinctions. I think these two versions show why. They involve some subtle distinctions about small parts about how one interprets the models in the theory, but don't actually necessarily make a big difference to the collection of models. So I can imagine Harvey Brown looking at me sternly, and Harvey asks me, don't you need to justify why the metric has chronogeometrical significance? That is to say, why the metric represents times, durations, lengths, distances. So the way that I want to answer the query is that the justification is the same as for any model-based representation in science. The metric represents durations, it represents lengths, and so on, by our stipulation. To give you an example, here with my fist, this fist, I'm going to represent the sun. Here with this fist, I'm going to represent the Earth. And here I have a very crude model of the Earth's orbit. Can you see it? Yeah, okay, good. Okay. Do I need to justify why my hands have planetary significance? The justification is that I've stipulated it in my modeling. Now, it's important that there's nothing about the substrate of a model that makes it represent. There's nothing about my hands intrinsically that make them planetary. Similarly, there's nothing about the mathematical models of general relativity and the metric itself that makes it spatiotemporal. What makes it is our representational stipulation, just as when we do other types of model-based science. Now, that doesn't mean that the work is done. Oftentimes, we should justify why a particular representation is faithful to the phenomena we want to represent. We should check that it represents not more structure than it desires. We should check that it represents accurately. This involves work to show that particular representational choices actually do reflect our intended interpretation. This is a part of the dialectic that I mentioned methodologically at the beginning. So this is what I take the goal of a paper that I wrote a number of years ago to be, right? This paper from 2013 about Lifeclocks, I take as a justification for why the representational stipulation we've made about how to represent durations in general relativity is a good one. It's a good one because it takes a very simple model of a clock that involves, in this particular case, light, but really any sort of material messenger bouncing between two mirror-like surfaces as a sort of clock mechanism. Now, this sort of work is not the only type of thing that can be done to justify why the representational postulates of general relativity are good ones, why they are representing the things that we want them to. Others have done other sort of work. In the 60s and 70s, there was interesting work done, for instance, to try to show why and how the different components of the metric, of the Riemann curvature tensor, all sorts of particular bits and pieces that are significant in the theory are really represent structures, durations, and lengths that we think that they ought to. So there's a contrast here on this interpretational strategy with another type of interpretational strategy that Harvey Brown and James Reed have suggested. So on their approach, right, and here I'm just going to read a quote from this very nice handbook article that they have published this last year, that locally in general relativity, assuming one's experimental apparata are sufficiently insensitive that curvature effects may be ignored, not only does the metric field take the form of the Minkowski metric field, that's the one that we find in special relativity, but the dynamical equations for matter field take a special form, Poincare invariant form. As a consequence of this, rocks and clouds built out of matter locally survey the metric field. The idea here is that we have this particular principle, which requires the matching, right, of certain symmetries of equations locally. And then we use that matching to between the equations for matter and the metric field to give an interpretation of the metric field in terms of the behavior and dynamics of the matter. So on this interpretation, instead of interpreting the metric directly, as I've attempted to do, you interpret it indirectly. by showing how it reflects a certain sort of structure that's familiar from special relativity. Now, the interesting thing is that this sort of interpretation has been discussed. This way of interpreting general relativity has been discussed at various other places. I discovered a couple of years ago a very interesting survey article by Jurgen Reis from the 1970s, where he discusses this way of interpreting general relativity. After describing in slightly different technical terms how it works, he says that this way of interpreting the theory can be used to reduce the physical interpretation to general relativity, at least for most concrete purposes, if not in a theoretically completely satisfactory way, to that of special relativity. Right? That's the basic structure, interpretive structure that I'm drawing a contrast with right now. Ehlers didn't entirely elaborate explicitly what he meant by most purposes and why he thought that it wasn't theoretically completely satisfactory. We can deduce a few reasons, though. One has to do with a certain vagueness in it. One is that the way in which general relativity and special relativity have this local correspondence is only a matter of approximation. Second, which is not often recognized, the way in which they correspond is unique. There are many different correspondences that we can make that all satisfy certain levels of approximation that are demanded. That makes the correspondence, the interpretive principles, a bit vague. Another is that it's restricted. It only applies to local quantities, and it does rule out certain matter models that we might be interested in considering. Matter models that don't satisfy the strictures of this strong equivalence principle. We also want to interpret collections of events in general relativity that are not just local, but that are extended. We might want to say things about what general relativity says about the possibility of time travel, where we travel in a loop of events from one event back to the same. Or we might want to say what general relativity says about the end of time, as we might describe the nature of singularities. There's a sense in which also it uses the resources of a less fundamental theory to try to interpret a more fundamental theory. We know that special relativity is a successful theory, but we know that general relativity is a more accurate picture of the world. We can interpret a more accurate theory with a less accurate one, but it makes it difficult to offer an explanation in that way of how the less accurate theory, special relativity, was successful. It suggests that there's a certain sort of circularity in the explanation. There's an interesting comparison here with Bohr's doctrine of classical concepts. You might remember that in the old days of the interpretation of quantum theory, there is this idea that we had to interpret quantum theory, at least in part, through a collection of concepts that we find that are roughly what we find in classical physics. Not exactly. That's not exactly what Bohr meant by classical concepts, but roughly the idea is that we have a collection of concepts that are classical, that are concepts native to the way that we did physics and phenomenological physics before quantum theory, that we use to interpret the results of quantum theory locally. What I mean by locally is for particular experiments. And the way that we do that in particular experiments varies by experiment to experiment. In the same way here, as we interpret local regions differently, depending on the experimental apparatuses that we have. One of the things that is difficult about that, though, is that we would like to think that quantum theory is a more fundamental theory. We want to use quantum theory's native conceptual apparatus to explain why classical mechanics was successful. And one gets the suspicion that any sort of explanation might have maybe not a vicious circularity, but some sort of undesired circularity to it, if we are only able to interpret the theory using classical concepts. Another issue has to do with the fact that interpretational correspondence needs more than mathematical correspondence. One of the things that we learned from Harvey that's exactly right is that you can never just look at a mathematical object and know what it represents. Right? Lots of mathematical objects of the same form represent all sorts of things. Just because we have a matching of symmetry groups of these two structures doesn't necessarily mean that the interpretations of them have to be the same. We need to have some prior way of interpreting the spatial concepts and the concepts of change and the temporal concepts that the two are using in order to compare how they can be approximated with one another. I want to emphasize something though. None of these four is anything like an inconsistency to it. When we have an interpretation that has these features and it's the only one that we have, we shouldn't reject that interpretation. But they are nonetheless features that are altogether comparatively undesirable. If we have an interpretation that doesn't have these features, it should be preferred to one that does. So what I'm suggesting is on these four features, right, these are four comparative reasons why the direct interpretation that I've given is comparable to an indirect one that goes through the local interpretation of GR through special relativity. Another contrast that you might draw is this fascinating idea that Eleanor Knox has suggested called Spacetime Functionalism. You might be wondering, what's the relation of Knox's idea to the ones that I've been suggesting? So here's a quotation from her paper recently on the topic. Spacetime is, according to this doctrine, whatever serves to define the structure of inertial frames. These are frames of reference that tell us which of the curves are force-free and therefore satisfy a kind of Newtonian first law. Inertial frames are those in particular in whose coordinates the laws governing interactions take a simple form, and with respect to which free bodies move with constant velocity. That's the explication of inertial frames that I just gave. Now, in the interpretation that I've given of general relativity, I haven't talked about inertia at all or inertial frames. One of the reasons why I haven't done that is that these are concepts that apply most directly to point particles. And as I've explicated, point particles have a kind of dubious status in general relativity. We can include them, but I don't see them as central to the interpretation of them, as, for example, material fields are. Another reason is that even though I have many sympathies philosophically with functionalism generally, it's not obvious to me that functionalism about space-time structure, in contrast to a kind of direct interpretation of space-time structure that I've given, is preferable. One is that in the specific type of functionalism, the specific function that Knox picks out, it seems too narrow, for instance. Temporal orientations, for instance, don't pick out inertial frames. Nonetheless, we would still like to call them aspects of space-time structure. But in certain cases, that they're also too broad. Certain types of matter fields that we can write down for a theory provide us with resources mathematically to define another set of inertial frames that are in conflict with the ones that are defined by the usual metric. Which ones do we pick? They both define structures of inertial frames. We want to pick the ones that's associated with the metric, but functionally, right, they represent the same sorts of structures. There's a general complaint though. Usually when we advocate for functionalism about something X, we do so in a set of models that presupposes a way to represent the putative role of X in those models. So for example, in the role that Knox talked about in the quotation, that role involves already reference to constant velocities. What is a velocity? It's a change of physical position over time. Unless the theory is already representing positions and times, there's no way to identify which structures fulfill that role. So there's a sense in which on this sort of approach, one already has to have some sort of representational principles for durations, change, and lengths, even to apply functionalism. If that's the case, one might as well go for the direct route that I've given. Okay, how am I doing on time? All right, I've got about 10 or 15 minutes. So let's go on now to dependence. there's a few different types of dependence we might be interested in. One type of dependence is determination. So determination is a kind of functional relationship. The determiner acts as a kind of argument to a function, and the thing determined is like the value of the function. Right? And remember, functions are single valued. You plug in the argument, you get a single thing out. In spacetime theory, we've got the following situation. The collection of spacetime structure and the matter fields, this quadruple that I've given up at the top, clearly determines the spacetime metric. It's just a part of it. The Einstein field equation tells us how the spacetime metric, G, then through the procedures that I've alluded to before, determine a covariant derivative operator. And associated with that covariant derivative operator are all the machinery that we need in order to define the Einstein tensor, including curvature tensors. So this R here in particular is the Ricci curvature tensor. So through that procedure, G determines R. The Einstein field equations show that R determines T. Remember, T here is the local energy and momentum in space-time. And one can also show that the determination of T also describes R. Now, so there is this two-directional determination between part of the curvature and the presence of energy and momentum. At the same time, the equations of motion for the matter fields, which typically involve space-time structure in addition to the matter fields, also determine the presence of energy and momentum. So that's this last arrow going from this quadruple down to TAP. Now, lots of things are determined here, but one thing that is not determined is the relationship between the space-time metric, the space-time structure, and the matter fields. What's going on inside that quadruple, in other words? What's the relationship between these things? Are there any dependence relations between them that are not determination relations? I think that there are, but the situation is a bit subtle. So let's say that y depends locally on x at a particular element in x within some particular set that we're considering. Just when all the different values that y can take on when you fix x is strictly smaller than all of the values that y can take on at that particular value. If you want to think about it intuitively, the idea is something like, if you have a correlated set of objects and you pick one from the first collection, if your choice restricts your options in the second, then there's a dependence. And similarly, for the second with the first. Now, everything on this view is going to depend on the collection of events. Typically, matter and space-time structure are going to mutually depend on each other in this way. If you fix one, it's going to restrict the options for the other. If you restrict space-time structure, it restricts your options for matter. If you fix your matter, it's going to restrict your options for space-time structure, but not uniquely. If it did so uniquely, it would be a determination. Why do I say typically? The reason why I say typically is that it depends on the equations of motion of the matter. Matter doesn't always depend even locally on space-time structure. An example is so-called topological field theory. This is a matter theory that only depends on the topological structure of the underlying collection of events. Doesn't depend on the metric, doesn't depend on a temporal orientation. All of that is irrelevant to that type of matter. Space-time structure doesn't always depend even locally on matter. An example that we've already discussed is test matter. Test matter, remember, right, has space-time structure enter into its equations of motion, but it's matter that doesn't contribute to energy and momentum. If you countenance such things, such matter doesn't, fixing such matter doesn't put any restrictions locally on space-time structure. So whether or not we have dependence between space-time structure and matter is a matter, if you'll excuse the phrase, of the particular dynamical equations for the matter, the particular equations of motion for them. And typically in most situations, in electromagnetism, modeling perfect fluids, most of the situations that physicists are actually interested in are situations where we do have this mutual dependence, but it's not a logical requirement. So if we restrict only to matters of dependence, we can ask the question about whether or not space-time, the structure, excuse me, whether or not, for instance, we should explain or understand a sort of dependence or a kind of relative fundamentality of the structure or properties of space-time structure like the metric as being prior to matter, or matter as being prior to geometry. Do we say that the metric is space-time structure because its properties in a certain sense are determined by or correlate with certain properties of matter? Or do we say that dynamical laws, right, for matter are constrained to refer only to the prior space-time structure? These are sometimes called, or at least these are very crude attempts at explicating on matters of dependence, these two ways of understanding how matter and geometry, space-time geometry, relate to one another. Now, on this sort of view, there's a sense in which it's like a both or a neither, depending on how you interpret things. I'm not totally satisfied with this, and I'm hoping you can help me out, but I'm going to give it a shot. So we do know that whatever space-time structure there is depends on, because it must include, whatever structure the matter dynamics presupposes. So in that sense, right, space-time structure does depend on matter. But matter dynamics also depends only on the space-time structure that there is. So the space-time structure constrains the dynamics, and the dynamics tell us what space-time structure is needed. Instead of understanding, therefore, these two, amongst these two as one being more fundamental than another, an asymmetric dependence where one depends on the other or determines the other, and not vice versa, we have a mutual dependence. Neither is more fundamental than the other. If we want to understand this in terms of a type of metaphysical explanation, we would have an explanation of the one by the other and vice versa. I'm going to skip over that. Now, here's something that I don't know how to answer. It's a part of the project that I haven't been able to answer yet. And I think it's just because I haven't thought about it long enough or deeply enough. What has to do with what is the nature of the dependence between these different things? I've talked about dependences as they're found in the models, but I haven't given an interpretation to what these dependences are. There's a bunch of options that I've listed up here for you. I'm not going to go through pros and cons for them. And the reason is because I'm not sure what the pros and cons are yet. If you have some ideas about what the pros and cons are for how to interpret these types of dependencies, I'd be really interested in hearing about them. I have my notepad up here, so I'm going to take it. The last thing that I want to come to is a kind of like bomb that James and Harvey and Dennis Lemkel dropped a couple of years ago about two seemingly miraculous coincidences that we find in space-time theory and special relativity and general relativity. The way James puts it, and this is slightly adapted from your actual words, but I think it's still faithful. How do you explain how all the non-gravitational interactions, that is to say, the equations of motion for material fields, are all, they all involve laws that have same symmetries. They all have Poincare symmetries. And also that these symmetries, right, coincide with that of the metric field. The reason why this is a coincidence is you might think that if all of these sorts of fields are on a par with one another, you might expect to have a zoo a variety of different symmetries, and yet you don't find that. And this is something that any interpretation of general relativity has to explain. I haven't mentioned these two yet. So one might ask, how does my interpretation respond to these two? There's a few things that need to be said though, right? So one thing that needs to be said is that I kind of reject the explanandum here. Some matter fields have dynamics that are locally invariant under a larger symmetry group than the Poincare group. So for instance, pure electromagnetism is invariant under conformal transformations. That includes not just the usual Poincare transformations, but also transformations that change the volumetric structure of space-time. The topological field theories that I mentioned before, even though they have less of a stronger pedigree than electromagnetism, are invariant under arbitrary diffeomorphisms. Some matter fields have a smaller symmetry group. The weak interactions, for example, are invariant only under the proper Poincare transformations. The ones that don't involve any time reversals or parity transformations. These are transformations that take left to right and vice versa. So we actually see a diversity of symmetry groups in our matter fields. They don't coincide. Okay, maybe I'm being a bit unfair. I think there is an interesting query in the conceptual vicinity. If you don't mind the reformulation, the question is, why do the dynamical equations for matter all depend on the metric or structures that it determines? Why that space-time structure and not a variety of different space-time structures? I do think that my interpretation gives a few different ways of trying to answer this question. The one that I prefer is that dynamics is about change over time. The metric represents time, and it determines the representation of change in models in GR. So the reason why they all depend on the metric and structures that it determines is that they all involve change, in particular, change over time, and the metric represents time, and the covariant derivative operator, which is uniquely determined by the metric, represents the notion of change. Yes, but isn't it a coincidence, you might think, that the dynamics for all types of matter can be described with a single structure for time? I think this is a deep question. It's a question which is not specific to general relativity, though. It's a question that we can ask about any theory of matter which is situated in space and time. Why is it that there is one time and not two times, for instance? When it's put that way, one response is to kind of throw the question back in the person asking its face, saying, well, what were you expecting? Is it really such a coincidence? There is a less condescending response, though. If there were a single unified matter field, as many folks working in extensions of the standard model believe, then there would be only one field that changes, and there would be no explanation needed as to the variety of different things. I want to emphasize that the notion of unification that's needed here is quite a lot thinner than the notion of unification that a lot of folks working in particle physics demand. The notion of unification here is merely some sort of ontological unification. You just have to regard matter as being of one sort that has many complex manifestations to it. It doesn't necessarily require a unification that involves, say, embedding the gauge group for the standard model into some larger gauge group. It can be something quite mundane as understanding the gauge group that we have as just representing a kind of multifaceted single material field. If that's the case, then there's nothing left to explain. I do think that it's an interesting question. If we were to regard theories that have more than one temporal structure, is there a way of rewriting them, a way of redescribing them with a single temporal structure, a single metric? If you assume the two matter theories, right, they have different times that they're experiencing, so different structures that are representing durations of coincident events for the two different theories. And those two theories interact with one another, or the matter that the two theories describe interact with one another. It seems that it might be possible to jointly describe the two using only a single metric, a single structure determining durations, where the differences between the two, or as originally described, show up as another type of space-time structure. This is just a speculation, though. I suspect that one will have to make some concrete assumptions about the types of matter fields involved in order to prove something about this. But if it's true, it would go actually some direction towards answering why it's possible and why it's always been possible to describe matter in terms of, and the changes of matter in terms of a single time. That sort of conclusion would go beyond the interpretation of general relativity to space-time theories of a general sort. I'll end my presentation here, and thanks for your kind attention. I'm looking forward to all of your questions.